So for the analysis topic of the structural portion, only determinant analysis is necessary. In all the indeterminate analysis that you may have learned in your undergrad or so on and so forth, that'll only be included on the civil structural PM exam. But for determinant analysis, essentially everything can be solved with three equations, and that's the sum of the forces in the x, the y, and the sum of the moments all equals 0. And those are the three equations with three unknowns, and that's determinant analysis. I'll talk a little bit more about determinancy here in a little bit, as well as talking about what determinant analysis really is, how you can use the beam formulas from the steel manual or some other exam to basically bring them together, knowing what you know to solve something you don't. Look at frames, and then look at trusses. So talking about connections, this is kind of an example of what you might see out in real world. In real world, you might see a connection, you're like this, and like, how do I analyze this? But this essentially is what we call a roller. And so a roller would be analyzed with this. The roller only supports forces in the vertical direction, and there's really no resistance in the lateral direction. But for resistance in the lateral direction, we have to look at what we call a pinned connection. And with a pinned connection, as you can see here, this is an example of a real world one, is there's lateral resistance as well as vertical resistance. But there is no moment resistance here. So this member could actually freely twist if it needed to about the axis. But in order to fix that, we have to go to a fixed connection, which basically eliminates movement, lateral, vertical, and rotational movement by fixing it at this point. So this is an example of a fixed connection that you might see in real life. Now I realize every one of these examples I've shown so far has been steel, but realize I could have done the same exact thing for wood, concrete, what have you. It just depends. I just wanted to basically introduce you to this and not just say, well, this is a roller. I wanted to be able to say, this is what a roller really looks like. This is how, as an engineer, you can use this. So going into what I was kind of hinting at earlier with determinancy. And so when we talk about determinant analysis, we're talking about with three unknowns here, with the three equations that we have. I have three equations with three unknowns. That means I can solve that. If I have more unknowns than I have equations, that makes the beam indeterminate. And for those of you taking the afternoon exam, you'll be dealing with indeterminacy a lot. And then the other one I want to mention to you is if you have three equations and you only have two unknowns, the beam is technically considered unstable. And there's also some special cases where the beam can be determinate and yet still be unstable. So resolving this top beam up here, we have a pinned connection which has reactions in the vertical and the lateral direction as shown here. Then we have a roller connection which has only a vertical reaction. If you ever hear the term simply supported, this is the situation they're talking about. And as you can tell here, we have three reactions with three equations, so this would be a determinate beam that you could easily solve. So here's some more examples of determinacy. We have our simply supported case up top, where we have three reactions and three equations, and that becomes a stable beam. Here I have four unknowns with three equations, which means this is 1 degree indeterminate. And then down below I have two unknowns with three equations, which makes this unstable. And as you can tell, the reason this is unstable is because if I applied a lateral load here, this beam would technically keep going. There's nothing to prevent that lateral translation. And so these are some special cases that I kind of indicated earlier. And so these would be determinate beams that are unstable. And so if I took this continuous beam right here and I analyzed it with three rollers, well, you would say, well, there's three unknowns with three equations, which makes that determinate. Well, it is determinate, but it's unstable. And the reason it's unstable is because all of the forces, or all of the reactions, act parallel to one another. So there's no lateral resistance to movement. And so that's why this one would be considered unstable. And so looking at the continuous beam below, we have three rollers once again. This should be a sign at this point. If you see three rollers on a beam and no pin, chances are it's unstable. But these all act to a certain point up here. And so if all the vectors from the reactions act to a single point, these are called concurrent reactions, which makes this unstable as well. But I do want to mention, I did bring up one term that I want to introduce. This is a continuous beam, is basically a beam that's continued across uh, with a support reaction in the middle. So there's one beam here continued across to another section right here. And so that's continuous beam. And so getting back to determinant analysis, this is the example I showed during the loading section. So what we're going to do right now is I'm actually going to go ahead and work through this analysis with you to kind of show you how determinant analysis works. And so if I use the LRFD load combinations, I can go ahead and resolve this into concurrent forces. And so I have my 2 kip dead load and my 3 kip live load. And so using the 1.2 dead load times that distributed dead load, and then the 1.6 load factor for the live load, I get 7.2 kips per foot. And that is the factored load for the live and dead load distributed load. And then looking at the dead load, I still have to apply that 1.2 factor to this 5 kip load. And notice I used 1.2 and not the 1.4. And the reason why is because for each member, once you figure out what the controlling load combination is, you have to continue to use that load combination throughout the problem. And so now we're actually going to go ahead and solve this. So the first thing I want to do is I want to go ahead and solve the forces in the x direction because there's only one force. And so summing the forces in the x direction, I only have x of a. And so x of a has to equal 0 since there's no force acting on it. And so that's the answer to this. X of a is 0. And so now I have a choice. I can either solve the forces in the y direction or I can take the moment. Solving for the forces in the y direction, I'll have 2 unknowns within that equation. And so what I'll wind up doing is solving r sub a in terms of r sub b, which works, but then I would have to use another equation to solve for r sub b, to solve for r sub a. Whereas if I just go ahead and take the moment about a, I don't have to factor in r sub a into this account, and I can directly solve for r sub b. And so the way we set this up is I basically sum all the moments about this point, and so I start looking at the forces in terms of my positive sign convention. So I have this 6 kip force 5 feet away from the A support, and that's acting in a negative direction. So that's where 6 kips 5 feet away, negative. And so going into the 7.2 kips per foot, I have this distributed load over the entire beam, so that's 7.2 kips per foot times 25 feet to get the total weight, and then I need a resultant of that. And the resultant of this load is right here in the middle, since this is symmetric. And so that would be 12.5 feet. And then I also have the reaction of B acting in a positive direction, as shown by the positive sign convention, 25 feet away. So when you actually solve for this, the reaction at B is about 91.2 kips. Then going back into summing the forces in the y direction, now that I know r sub b, basically what it winds up being is r sub b acting in a positive direction, the 7.2 kips acting negative, and the 6 kip acting negative results in an r sub a of 94.8, which, doing a quick sanity check on this, because this 6 kips load is further to the left than it is to the right, you automatically know that r sub a has to be larger than r sub b. And so kind of taking this into another example, using a cantilevered section for determinant analysis. So with a cantilevered beam with only a fixed support on the left or the right, this becomes a determinant analysis because once again I have 3 equations and 3 unknowns. And so resolving this into the actual free body diagram you see below, we go ahead and put all the reactions into the positive sign convention. Now using the free body diagram, we're going to go ahead and solve for the reactions. So once again, the sum of the forces in the x direction only has x of a, so x of a has to equal 0. So looking at the forces in the y directions, we have a negative 6 kips acting downward, which is shown right here. And then we have a 7.2 kips distributed load acting downward as well. And so this 7.2 kips per foot times 10 feet plus this 6 kips equals 78 kips, as shown right here. So the reaction at A supporting these two loads will equal 78 kips. Next, we're going to go ahead and sum the moments about the support. And so this is the only moment right here resisting these two loads. And so we have a 6 kip load acting 5 feet away from the support, and we have a 7.2 distributed load acting 15 feet away from the load. And the 15 comes from 10 plus 5, which is half the load. And so with distributed loads like this, we just take half of the distance, and that becomes the resultant. And so half this distance plus this 10 feet equals 15. And so when you actually solve for it, you get the moment at A, or moment at the support, equal to 1,110 feet kips, or foot kips. So I also want to bring up another principle called superposition, which superposition is actually one of the fastest ways you're going to be able to solve things on the exam. And if you have a load table with you, either from the steel manual or from NDS, the wood specification, this will help you out significantly. So what we can do with superposition is we could take this beam and basically break it down into components and then add them up together. So the way this is going to work is I'll take the 6 kips, take one beam, and then I'll take the distributed load and put that on another beam. So in the end, what's going to happen is I could take the reaction from the point load and the reaction from the distributed load, add them together, and I'll get the same answer, as well as R sub B and X sub A. And so these are the two references I mentioned earlier. Both of these manuals have load tables in there for you to be able to easily calculate this without having to sum the reactions. And so using the NDS for this, so using our distributed load here and our point load here, we can go ahead and solve for the reactions. The reaction from a distributed load that's symmetrical across the cross section is WL over 2, and the reaction from a point load is PB over L or PA over L, where PA is this distance and PB is this distance. So essentially what it's doing is taking a ratio, and it's saying the closer this is to one support, we'll have a higher proportionate reaction than the further support. And so looking at the previous example, using that, we have the reaction at A using the first equation, which is 7.2 kips per foot times 25 divided by 2, plus 6 kips times 20 feet divided by 25 feet. Once again, that's that ratio we were talking about, and that'll equal 94.8 kips. Similarly, using the same rationale for the reaction at B, we wind up with 91.2 kips, which is the same answers we found from actually going through the analysis wholeheartedly. So the next thing we're going to talk about is frames. And so frames can come in multiple different varieties. You have this traditional frame structure, which has a pin and a roller connection, and then you also have this frame right here, which basically looks like a T. Both of these are considered frames, and the analysis basically goes that we have to factor in how the load transfers from this beam into this column here, and the same similarly over here. And so one of the ways we'll look at this is you'll either see two different ways that frames are done. You'll either see an internal hinge at the translation between the column and the beam, or you'll see a fixed connection at the transition. And so when we talk about the internal hinge, we have to use the internal sign convention for it. And so the vertical force here becomes the vertical force here, and then the axial force here becomes the axial force here, or the X force there. Sorry, just trying to make sure I got this correct for you. But the idea is we need to make sure we're translating the loads appropriately. And as you could tell from the arrows, these need to be equal and opposite. And so going over here to the fixed connection, you'll see the same thing going on. And so the two moments are acting in opposite directions from each other. So that way when you sum the moments about here, you wind up with 0. And then similarly, if you add the vertical forces together or the axial forces together, you should wind up with 0 as well. But these forces will transfer from one end of the beam over to this column and then down to the support. And so just looking at this example here, I want to show you how loading affects different things. And so someone may say, we want to analyze this with a 5 kip distributed load. And we're like, well, this has got to be the worst load case because, well, it's covering the whole beam. But I just want to show you how this little load right here can actually cause more havoc for us. So looking at this, what I want to show you is solving with the reaction at B and the reaction at A. For this one, we have the reaction at A at 33.3 kips, and that's acting in the vertical positive direction. Whereas looking at this one, we have a reaction at A equal to negative 4.2 kips, acting in the downward direction. And so the whole reason I'm getting at this is this beam will cause a huge negative moment when we actually analyze it across this section of the beam. And so that completely changes how we actually design the beam. So if we're looking at concrete, that specifically addresses where we're going to place the rebar. And I'll talk about that a little bit more when we start talking about doing moment diagrams and when we actually talk about how we're going to design the members. So the next big one you're probably going to see on the exam, in fact, I can all but guarantee it, is you will see a truss problem. And so there are a couple assumptions we make with trusses we assume at the members that are pin connected. And we assume that loads are only placed at the nodes. And we also assume that the forces in the members themselves are only axial loaded. And so there are actually two methods for analyzing trusses. There's the method of joints and then the method of sections. And then later what I'm going to talk to you about is identifying zero force members, which should help you streamline this whole analysis process. And so we're going to go ahead and use this truss example throughout this next few slides. And so the problem that we're going to have right now is we're going to try and find the force in CJ, which is this member right here. And so with method of sections, the way we're going to have to do this is we're going to have to solve for the external reactions first and then break it down piece by piece until we get through this. And so solving for the reactions right now, we have the R sub G is 15 kips and R sub A is 15 kips. And the reason why they're equal is because we have symmetrical loading about the cross section, which if for whatever reason I wound up with R sub A is 20 and R sub G is 10, I would know something was wrong. I messed up the analysis, maybe put a sign in the wrong place or something. So every time we do analysis, we need to make sure we're doing sanity checks on our work to make sure that it kind of jives with what we're looking at. So if we have symmetrical loading, then the reaction should be the same. So starting the analysis with the method of joints, we're going to start by looking at node A and start working outwards towards CJ. So one of the problems with the method of joints is it's very cumbersome and you have to do everything sequentially in a pattern. So starting with node A, notice I only have two equations here, and so I can only handle two unknowns at one time. And so with node A, I can't just jump to node B because I don't know BC, I don't know BI, and I don't know BH. However, I can solve for A and jump to H because I know I know what AH is, but I don't know HB or HI. And so those would be my two unknowns to go with my two equations. So we're going to go ahead and solve for the reaction or the members at node H by basically taking the sum of the forces in the y direction at node A, encompassing the reaction at A, and we would encompass XA if there was a force there. So summing the forces in the y direction, we have R sub A acting upwards, and we also have A sub H acting upwards. As a special note, whenever we handle truss analysis for positive sign convention, we always assume the members are acting away from the node. And this positive sign convention indicates that we assume the members are acting in tension. So AH in tension, using similar triangles to get the y component of it, we go ahead and use 8 feet over 10 feet, which equals 0.8. So 0.8 times AH equals negative 15 kips. By solving that, AH is going to wind up being negative 18.75 kips. And as I mentioned before, the positive sign convention going away from the node indicates tension. So if the node is actually coming, or the member is actually going towards the node, then we assume the member is now in compression, which makes sense looking at the structure here on the right, because we have the 10 kips acting downward, which means this force is going to be transitioning into here, and potentially into here as well. But we'll find out when we actually solve for HB here in a little bit if that member is in compression as well. So solving for AB, we only have two forces in the x direction. We have the x component of AH, and we also have AB. So now we can go ahead and say AB is positive, and we go ahead and mark AH as negative since we just realized it was in compression. Similarly, you could also say AH is in positive as well, and then just when you actually insert the force, indicate it's negative. It's kind of up to you to decide how you want to do it. However, this time I chose to just go ahead and make this negative and insert it as a positive force. But however you do it, just make sure you keep your signs straight, because otherwise it'll completely change up whether something is positive or negative in terms of whether a member is in tension or compression. So as I said earlier, we're going to work up to node H at this time. And so we're going to go ahead and solve for HB and HI. And as you notice, I did include the 10 kips at this node. So anytime there's a reaction or a load acting at a node, you must include it in the free body diagram. So summing the forces in the y direction, we go ahead and solve that HB is 5 kips in tension, which means that HA is carrying all the compression from the 10 kip load. So the summing the forces in the x direction, using the x component of HA and HI, we wind up with HI as 11.25 kips in compression. So now working down to node B, we have the sum of the forces in the y direction. We have BH and BI as the only forces in the y direction. So BI is going to wind up being 6.25 kips compression. And the sum of the forces in the x direction, we have BC, BA, and the x component of BI. So solving for BC, we wind up with 15 kips in tension. Moving up to node I, we have IH, which is known, we have IB, which is known, and then we have IC and IJ, which are unknown to us. So we'll be solving for these two using our two equations. So summing the forces in the y direction, we have the y component of IB and IC. And so we have this one acting in compression, we have this one acting in tension, or assumed tension at this point. But when we actually solve for it, we find out that IC is acting 5 kips in tension. Summing the forces in the x direction, we have IH, IJ, and the x component of IB. And so we have IH and IB acting positive direction as well as IJ. So you know one of these is going to have to be in compression, which winds up being IJ. So IJ winds up being 15 kips compression. So working through all of the nodes, we finally get to node C, which includes the member that we're trying to find in the first place, CJ. So looking at this free body diagram here, we notice that CI and CJ are the only forces in the y direction. So using the positive sign convention, we have CJ times 0.8 plus CI acting outwards. So looking at that, you automatically have to know that CJ has to be in compression to balance out this force and allow the forces in the y direction equal 0. So CJ equals 6.25 kips compression, which if you remember back, BI over here was also 6.25 kips in compression. So because these are repetitive members like this and the loading is symmetrical, you should expect that. And so also I didn't need to do this, but I did anyway. The sum of the forces in the x direction, just to finish this out, is 18.75 kips tension for CD. And so one thing I will mention, since this is symmetrical again, this force here should equal this force, as well as BC should equal EF, and AB should equal FJ, or FG, sorry. And the same goes for all the other members that are symmetrical on the other side. So now I showed you the method of joints, and I'm sure what you're probably thinking is, why would I have to do that on a test? There is a simpler way, and it's called the method of sections. And so the rules for making cuts or using the method of section is the cut must separate the structure into only 2 parts. It cannot pass through more than 3 members and cannot result in members with concurrent forces. And so right now what I'm doing up here is I'm trying to make sure I stay true to all 3 rules by cutting right here. And so if I cut right here, I have one structure here and 2 structures here. Ideally, I also have 1, 2, and 3 members only that I'm cutting through, and I have these two forces acting concurrently, but I have this diagonal force here that provides a vertical component. So rule 3 is not violated using this cut. As we did with the method of joints, before we start the method section, we do have to solve for the external reactions. Before I actually can solve for the members of the cut, I have to solve for the external reactions at x of a and r sub a. And so after I make the cut, essentially what I'm going to do is use these support reactions as well as the members exposed by the cut to solve for these members. So what I'm going to do is take the sum of the forces at the y direction, since C sub j is the only exposed member here acting in the y direction. And so from doing that, we have R sub a acting in the positive direction, we have negative 10 kip load acting downward, and then we have Cj, which is assumed as in tension right now, acting upward. And then once again using similar triangles times 0.8. So we have 0.8 C sub j, or Cj, equals negative, or 10 kips minus 15 kips, which is a negative 5 kips. So finally, Cj equals 6.25 kips compression. And so this is the same exact answer that we got using the method of joints. It's just method of sections streamlined this whole process. Method of sections is ideal for members in the middle of a truss that you have to solve for, especially if method of joints would take prohibitively long time on an exam to get to it. However, there are situations where you will be forced to use method of joints, particularly if the member was such that cutting it would violate one of the 3 rules, or if the member was right here, like A sub h, solving for the forces in that member. Then method of sections wouldn't make any sense. So one thing I will mention to you, as I kind of alluded to earlier, there are zero force members in trusses typically, and they usually occur by analyzing, when you look at the node, if there's only if one axis consists of only one force, then that force must be zero. And then similarly, if one axis consists of 2 forces, those forces must be equal and opposite. So as an example of this, we'll look at node D. And node D has one force acting in the y direction, and that's member DJ, so that force must be 0. Looking at the x direction, we have CD and DE acting in the x direction, so those forces must be equal and opposite to counteract one another. Looking at another example, we're going to go ahead and identify all the zero force members in this trusses. So the first thing we're going to do is look at nodes F and J. Looking at node F, we have two forces. We have one force in the x direction and one force is in the y direction. So based on the equations we've used in the past, the sum of the forces in the x direction and the sum of the forces in the y direction have to be 0. Therefore, you know these two members have to be 0. And since this is the symmetric truss as well, you can look at node J and say the same thing, where members IJ and JE have to be 0 as well. The one thing I will mention about this, had there been another load placed at this node, either in the y direction or the x direction, it would change this. So if there was one in the vertical direction, then E sub j would have to be non-zero. However, I sub j would still be 0. Looking at nodes B and D, we have the same situation set up here. We have one force in the y direction, so we know that force has to be 0. So remember, BG and DI are 0 force members as well. So after identifying those 0 force members and removing them, we're left with the structure on the right. And we can solve this structure and for each one of the members, as these are the only members that are non-zero. And we'll get the same answer.